Hi, my dear students. For the last couple of classes, we were discussing software effort estimation techniques. We already discussed the techniques such as top-down estimation, bottom-up estimation, expert judgment, estimation by analogy, then function point analysis, both Albert function point analysis and function point marks 2. Then object point estimation or object point analysis. And here we are going to discuss the last software estimation technique, COCOMO model. COCOMO, constructive cost model or cost constructive model, a constructive model. That is COCOMO. We shall discuss COCOMO in detail here. COCOMO model is referred in the literature of software project management as constructive cost model. Constructive cost model. It is a parametric productivity model. A model based on parameters. Several parameters are passed for the software estimation. Bohm's COCOMO or Barry Bohm's COCOMO is particularly related with software estimation. It refers to a group of models. Barry Bohm originally based his models in the late 1970s on a study of 63 projects. Out of the 63 projects, only 7 were business systems, and so the models could be used with applications other than information systems. The basic model was built around the equation effort is equal to C into size raised to K. Effort equal to C into size raised to K, where effort was measured in PM. PM means the number of person months consisting of units of working hours. Size is measured in KDSI. KDSI means kilo delivered source code instructions or thousands of delivered source code instructions. Size was measured in KDSI. C and K are constants. The basic model was based on the equation effort is equal to C into size raised to K. The first step is to derive an estimate of the system size in terms of KDSI. Derive an estimate of the system size in terms of thousands of delivered source code instructions. The constants C and K depended on whether the system could be classified as organic systems, semi-detached systems, or embedded systems. BOM termed or BOM classified the system as an organic or a semi-detached or an embedded system. This related to the technical nature of the system and the development environment. The first classification is organic mode. This would typically be the case when relatively small teams developed software in a highly familiar in-house environment and when the system being developed was small and the interface requirements were flexible. Organic mode means the development team is small teams. They develop software in a highly familiar environment. Also, the interface requirements were flexible. Then second one, embedded mode. This means the product being developed had to operate within very tight constraints and changes to the system were very costly. It means that embedded mode means that the developing software has to operate within very tight constraints. Also, any modifications to the system, any changes to the system were very costly. Third classification is the semi-detached mode. Semi-detached mode combined elements of the organic and the embedded modes. Or semi-detached mode had characteristics that came between the two above classifications, organic mode or embedded mode. The exponent value k, when it is greater than 1, it means that larger projects are seen as requiring disproportionately more effort than smaller ones. This reflected Bohm's finding that larger projects tend to be less productive than smaller ones because they needed more effort for management and coordination. Bohm, in fact, found this by itself to be a poor predictor of the effort required and so went on to develop the intermediate version of COCOMO. It took into account 15 cost drivers. In the intermediate model, a nominal effort estimate is derived in a similar way for the basic model. The nominal estimate is then adjusted by a development effort multiplier, where development effort multiplier is calculated by taking into account multipliers based on the effort drivers. These effort drivers are either product attributes, computer attributes, personal attributes, or project attributes for various driver types. It is shown in the table. In the first type, product attributes, the cost drivers are required software reliability, database size, and product complexity. In computer attributes, the cost factors or the cost drivers are execution time constraints, main storage constraints, virtual machine volatility. It means that the degree to which the operating system changes, and computer turnaround time. There are four various attributes or factors, computer attributes that drive the computer attributes. Then third type, personal attributes, personal, analyst capability, application experience, programmer capability, virtual machine experience, and programming language experience. Five various cost drivers that drive personal attributes. And the last one or the fourth driver type is project attributes, use of modern programming practices, use of software tools, required development schedule. Three various project attributes or three various factors that drive the project attributes. These multipliers take into account such influences on productivity as Bohm's suggestion that having a programming team fully with the programming language, provisioned with the programming language to be used could reduce the effort required to implement the project by up to 20% compared to a team with a very low or initially non-existent familiarity with the programming language. In fact, the biggest influence on productivity according to Bohm is the capability of the implementation team. A new family of models refined by Barry Bohm and his coworkers on 1999. It is named as COCOMO II or COCOMO II. It uses various multipliers and exponents, the values of which have been set initially by experts. A database containing the performance details of executed projects is being built up and periodically analyzed so that the expert judgments can be progressively replaced by the values derived from actual projects. The new models take into account that there is now a wider range of process models in common use for software development projects than in the late 1970s and early 1980s. Estimates are required at different stages in the system lifecycle, and COCOMO II has been designed to accommodate this by having models for three different stages. The first stage is application composition stage. Application composition, where the external features of the system that the users will experience are designed. Prototyping will typically be employed to do this. With small applications that can be built using high productivity application building tools, development can stop at this point. Then second stage is the early design, where the fundamental software structures are designed. With larger, more demanding systems, where there will be large volumes of transactions and performance is important, careful attention will need to be paid to the architecture to be adopted. Then third stage is post-architecture, where the software structures undergo final construction, modification, and tuning to create a system that will perform as required. To estimate the effort for application composition, the counting of object points already we have discussed earlier. It is recommended by the developers of COCOMO II. At the early design stage, function points are recommended as the way of gauging a basic system size. A function point count might be converted to a source line of code equivalent by multiplying the function points by a factor of for the programming language that is to be used. The qualities that govern the exponent drivers used to calculate the scale factor are listed below. The less each quality is applicable, the bigger the value given to the exponent driver. The fact that these factors are used to calculate an exponent implies that the lack of these qualities will increase the effort required disproportionately more on larger projects. The first quality is precedentness. This quality refers to the degree to which there are precedents. Similar cases in the past. There are similar cases, similar softwares we developed in the past for the project that is being planned. The greater the novelty for the new system, the more uncertainty there is, and the higher the value given to the exponent driver. The second quality factor is the development flexibility. Development flexibility means it is the degree to which the requirements can be met in a number of different ways. The less flexibility there is, the higher the value of the exponent driver. The next quality factor is the architecture or risk resolution. It relates to the degree of uncertainty there is about the requirements. If they are not firmly fixed and are liable to change, then it would lead to a high value being given to this exponent driver. The fourth quality factor, team cohesion, reflects the degree to which there is a large dispersed team as opposed to there being a small tightly a tightly coupled team. The large dispersed team perhaps may be in several countries. Process maturity. The last quality factor is process maturity. The software quality area already explains the process maturity model. The more structured and organized the way the software is produced, the lower uncertainty and the lower the rating will be for this exponent driver. In the COCOMO II model, the effort multipliers are similar in nature to the development effort multipliers used in the original COCOMO or the previous version we have already seen. There are 7 of these multipliers that are relevant to early design and 16 that can be used at the post-architecture stage. The 7 effort multipliers can be used in the early design stage, so they are named as early design effort multipliers or effort modifiers. The current table lists the effort multipliers for early design. They are product reliability and complexity, required reusability, platform difficulty, personal capability, personal experience, facilities available, and schedule pressure. As with the previous COCOMO or original COCOMO, each of these multipliers might be given a rating of very low, low, nominal, high, or very high. From very low to very high. 5 various values can be or ratings can be given to each of the effort modifiers. Each rating for each effort multiplier has a value associated with it. A value greater than 1 means the development effort is increased. A value less than 1 means effort to be decreased. The nominal rating means that the multiplier has no effect on the estimate and it will be 1. The intention is that the ratings that these and other values used in COCOMO II will be modified and refined over time as details of actual projects are added to the database. Post-architecture effort multipliers are product attributes, platform attributes, personal attributes, and project attributes. The project attributes contain required software reliability, database size, documentation matched to lifecycle needs, product complexity, and required reusability. Platform attributes consist of 3 various attributes such as execution time constraint, main storage constraint, and platform volatility. The drivers in personal attributes are analyst capabilities, application experience, programmer capabilities, platform experience, programming language experience, and personal continuity. And the fourth modifier type, project attributes, consist of 2 drivers, use of software tools, and multi-site development. These are the various effort multipliers that can be used in the post-architecture stage. So far we discussed all the software effort estimation techniques from the bottom-up technique to the COCOMO II model or the COCOMO model. Okay, thank you.